Hello and welcome to my presentation on how our off-road racing team uses the simulation and topological optimization tools within Altair Inspire to design lightweight and durable components for our entry in the Baja SAE Student Design Series. I'm Thomas Neumaier. I'm the CNC lead for Case Western Reserve University Motorsports, as well as a member of our drivetrain subsystem. First, overview on the Baja SAE Design Series. Our team competes where we design, build, and race a single-seater off-road vehicle to race in a variety of challenges, as well as present in static events. In the dynamic events, we test the straight line acceleration over a distance of about 100 to 150 feet, test the suspension in either a pure obstacle course or in a combination obstacle maneuverability course known as Baja Cross, test the traction in either a hill climb or a sled pull. We test our handling around a maneuverability track. And finally, the car's overall performance in a 4-hour wheel-to-wheel endurance race to see who can lay down the most laps. In the static segment of the competition, we have to present our design as a prototype for a reliable, maintainable, ergonomic, and economic production vehicle to serve the recreational user market. In the business category, this comes to fruition where we pitch our design as a prototype to a panel of judges. Next, in the cost event, essentially how much it costs to build our car. And in the design event, we present a briefing as well as a presentation to a panel of judges who ask questions. And they're often industry experts who are often former Baja competitions. So a quick team breakdown. We have a team captain who is voted in each year, who, although leads the team, is also responsible for a lot of organizational things, such as assigning subsystem leads. So we have our brake subsystem, who designs all the brake and throttle components, including hydraulic systems. Frame team, who bends, notches, and welds the design of our chassis. Suspension and steering, design the geometry and the components such as uprights, steering rack housing, as well as tuning our air shocks with shim stack and pressure testing. Next is our DAC team, data acquisition. They handle all the electronics on the car, from brake lights to the data collection systems with Hall effect sensors and IMUs, and even our four-wheel drive actuation system. And a new distinction this year is the testing subsystem, which works closely with our DAC team to formulate tests to effectively collect that data. Next is our drivetrain and CNC team. We handle the design of essentially all rotating components except for the engine, which is in the rules. We can't mess with that. This includes our custom gearbox, which I'll get to later. And a more recent distinction is that the CNC team has distinct leadership, since the transition to four-wheel drive has put such a heavy load on this subsystem. And finally, our panels and ergonomics team, who handle all our panels, our seat, and our livery. They're essentially our composites team, as much of their work is done in carbon fiber. And now an overview of our design process. So a big part of our mission statement is that we make a new car from scratch every year. Although designs can roll over from year to year, we manufacture each part every year, which puts an emphasis on design for manufacture, as we know what is easy and what is hard to make. So it depends whether it's an iterated component or a new component, whether we are evaluating a failure mode. But here we can look at what went wrong or what we can improve on the next car. So then we move into identifying our requirements and how our part can fulfill these requirements before moving into the conceptual design phase, where we come up with our general geometry, preliminary calculations to prove the concept, as well as choosing generally how the parts could be made. We present these designs to general body, and we get feedback on our designs from our faculty advisor before moving into the detailed design phase. Here's where we finalize geometry, and we also simulate our loads to make sure that the part will not fail under normal operation. And this is where Altair Inspire really comes into play, is under our simulation and our lightweighting. So traditionally we'll do this in SolidWorks, where there's simulation tools, but in Altair Inspire we can run our simulations, run our optimizations, and then rerun the simulation on our optimized design. So it's a very streamlined workflow, and so we've found a lot of success with that recently. One of our most recent successes has actually been in our gearbox. We run a fully custom gearbox. Our teeth are cut and ground by one of our sponsors, but we design the tooth profiles as well as our webbing and our gearbox housing. So starting out, we had this web design that has basically been here as long as I've been on the team, and even beyond. I think looking at previous year's designs, there's not much variation in the webbing, and this is rotating mass, but it's rotating in one direction. It's only taking load in the direction that we're driving the gearbox forward. We don't have a reverse gear, so we saw this as an opportunity to put the load in one direction and optimize for that direction. So we started in SolidWorks iterating with different fillet sizes and different thicknesses, but our results were unsuccessful for this single direction idea, having a webbing that is curved in the direction of the load. So we had more spokes and we alternated the angles, we changed the fillet sizes, and we couldn't find any worthwhile weight gain without significantly lowering the strength. So for this top design, 5% weight decrease, but we dropped our FOS below 1. So this design would fail under loading. And this design, although it has an FOS of 1.1, it only decreased the weight by 2%, and the manufacturing is crazy. We'd have to get small end mills in there to get those fillets. It would be very tough. We moved into Altair Inspire, and with help from Eric Larson, with trainings, we were able to start simulating our loads. Here you can see we have our outer section of the gear where we can apply our load. Then we left the webbing as a design space, and we constrain that inner spline bore to simulate the torque being sent and the wheels on the ground. And we were also able to implement cyclic symmetry constraint into our study, which allowed it to be more of a final design rather than having, alternating cyclic patterns that we would have to normalize, considering this loading is going to be happening to each tooth over the rotation. Our result was surprising. Symmetric webs are better. We had been hell-bent on this unidirectional idea, and the optimization came back that symmetric is better. So we took it into SolidWorks again, and we changed some of the hole sizes and the fillet sizes to make it more easily machinable. It increased the torsional strength, which is the most important, slightly decreased the radial strength, which is less important for our load case. And we were able to find a 12% weight decrease with an overall factor of safety of 1.2. Now, we did beef it up before manufacturing it just to have wiggle room, and we still got a weight savings of 5% while decreasing that machine time from that crazy multi-spoke design. And we had 0 failures. We ran this gearbox both in preseason testing for 2 months, 2 heavy load competitions with a lot of endurance race as well as suspension, and even this whole summer of testing where we ran the car off drops bigger than anything we've ever seen in a competition. And our transmission fluid was clear, no gear failures, so everything worked out great. And looking into the future, we're looking to make lightweighting a more intentional practice. So looking at our brake pedal, it's designed to withstand essentially the strongest guy on our team pounding on the brakes, full force to lock the brakes. And the collection of bores near the bottom allow for an adjustable pedal ratio as chosen by our brakes design and based on the driver. So the first attempts at weight reduction included shell pocketing on the left and drilling holes, the dreaded speed holes, which actually at our last competition, as you could see, led to a failure during a brake check, which is unacceptable. We ended up having to make a steel brake pedal, which is significantly heavier when it's essentially not needed. So we took our brake pedal into Inspire. We were able to partition our bores to keep that same design intent. We simulated maximum driver load, and we want to maximize stiffness this time. And we got a weight reduction of 60% with a minimum FOS of 1.5. And we took that design into SolidWorks and made it being able to work with our full car model. And our plan this year, we're very excited to work with a sponsor to possibly 3D print this in titanium so we could even further our lightweighting and get a super lightweight strength ratio. So I want to thank you for coming to my presentation, and also a huge thank you to Altair for giving us the opportunity to learn such valuable skills with industry-leading technology, and for giving us the chance to present to you today. Thank you.